Health, Psychology, and Human Nature with André Sturesson. Hey friends, hope you're having a great day. Are you following me on Instagram and Facebook? Please go to Health, Psychology, and Human Nature on Instagram or Facebook, or both for that matter, to get the latest episodes, inspiration, and more. Please take a pause and go there. Also, if you like the episode, please share it with a friend, family member, or somebody else who you think might like it. Welcome friends to Health, Psychology and Human Nature with André Sturesson, a science-focused podcast where we explore, learn and improve our lives together. Are we born with an intuitive understanding of numbers, or is it something we learn later in life? In today's fascinating episode, we discuss the number instinct, what it is, how it's traced back evolutionarily, the biological underpinnings, and more. To learn more, read Andreas' book, A Brain for Numbers. Andreas Nieder is a professor of animal physiology and the director of the Institute of Neurobiology, University of Tübingen. Friends, please enjoy. Welcome to the show.
It's my pleasure.
I'm very, very happy to have you here. You have done some fascinating research. I'm really glad to have you on to talk about it.
Well, thank you very much.
And from what I understand, I think our names also means the same thing. Both Andreas and André both mean man, right?
Yes, the manly.
Yeah. Are we manly?
I hope so.
Yeah.
Hope so.
Me too. Okay. So you've written a book and it's called A Brain for Numbers, the biology of the number instinct.
That's right.
Yeah, so it's very fascinating. And I would like to just start off by asking, what is the number instinct?
The number instinct is a very intuitive or spontaneous capability to comprehend and understand numerical quantity, and sometimes even to calculate with it right away. So the idea is that we don't have to learn to deal with numbers, but we understand it automatically, more or less based on how our brain is wired.
Right. So it's more that it's built into us like a numbers system that we get from biology instead of something that we learn later on in life.
That's right. It often is also called a number sense. So with number instinct, I really mean this number sense. And of course, it is a very rudimentary, very basic understanding of numerical quantity. But nevertheless, there's plenty of evidence that we are able to understand numbers in this very basic sense, even without learning.
That's super interesting. And how like what kind of things have been researched to be able to find this out?
Yeah, there are a couple of very interesting lines of research. I think the one that is very fascinating to many people is the research in infants and little children.
Right.
I guess we all know, or we have to remember, that we painfully learn to deal with real numbers, natural numbers, and to learn counting. And we learn this at about the age of 4 on average. But even before, babies and infants can discriminate set sizes. So they can discriminate different sets made up of different objects or events. And originally, this has been discovered and shown in babies of a few months of age.
Yeah.
But the most or the youngest subjects that have been investigated are 50 hours after birth.
Whoa, that's early.
That's very, very early.
Yeah.
And these are little infants that can't sit, of course. they are hardly mastering their senses.
Yeah.
But at the same time, developmental psychologists tell us that they can discriminate set sizes already.
Right.
And of course,
with set sizes, what do you mean by set sizes?
with set size, I mean cardinality. I mean the number of objects in a set.
Okay. So like being able to count, like there are 3 berries here or 3 toys or whatever.
Yeah, exactly. But I would not call it counting, because this is exactly the capability that kicks in when we learn to verbally, symbolically count, and then we can say 1, 2, 3, 4, 5, 6.
Right.
But this is actually not this capability that we are learning only when we are about 4 years of age, but an understanding before. So it is a non-symbolic understanding of how many objects belong to a specific set or are part of a specific array.
Okay, so it's kind of if it's a particular object. So let's say if it's
dolls have been used in the beginning. So how many dolls are on the stage, for instance?
Okay, yeah.
And right. in more recent times, there have been used more controlled objects like dots of different sizes and diameters and so on and so forth on computer displays.
Okay, so it's been able to. So it's an intuitive sense of how many dots are on the screen. Yes,
and being able to differentiate the number of dots in one set from the number of dots in another set. This is sort of the hallmark or the core of this number instinct or number sense. That's what this is all about. But importantly, it's not just l'art pour l'art. It's really connected to our later capability to learn counting with symbols.
Right.
And that's what's making it interesting, also from a research point of view. So this is a capability that is tied and connected to our counting capabilities.
So it's like an underlying foundation for being able to count.
Exactly right. That's how I would call it. A basis that sits there in our brain and in our behavior and waits whether it will be expanded once someone is around in our culture to teach us real counting, which again takes a few years until we really master this. And I guess we all have our memories from school, mathematics.
Yeah, yeah, I do. Yeah.
But even before this system tells us what numbers mean, so what their quantitative meaning is, and then later we learn to map this onto symbols and numerals.
Right. So first we have the intuitive sense of, okay, so there's 3 circles on the screen or 5 or whatever. And then after that, you learn that the abstract number or the sign for 3 is connected to that foundational.
Yes. And then counting is becoming a real full-blown symbol system, like language.
Right.
And that's something we would not find earlier, or we would not find in animals or in infants yet.
Yeah. That's really interesting. And is this also what is the foundation of what we later use in life when we're doing a lot more advanced mathematics and similar things?
Even advanced mathematics, in terms of where it is represented in the brain, and also in terms of its fundamental characteristics, shares these signatures with the number instinct. Yes. And this is one of the most convincing evidences, actually, that these two systems talk to one another,
right? And
they rely on one another.
Okay, so what you're saying is that it's really 2 different systems. We have this inbuilt, intuitive, foundational system for recognizing how many objects there is, and then we have this other, more abstract system, which is more about symbols, and it's also more about like a language almost, where we subtract and we multiply, etc.
Yes, exactly. I think you could compare it, if we talk about language, you could compare it with vocalizing, making vocal utterances as a basic form. And this is a different system compared to our speech and language capability.
Right.
But both of them use specific characteristics that are fundamental to both of them.
Right. And what is quite interesting about this is that it's also traceable through evolution, right?
Yes, that's very interesting, particularly for me as a biologist. And so I like to work with animals and try to find out whether there are some precursors that evolution has endowed animals even before humans arose on this planet. And the lessons is that actually all animals that have been investigated in a thorough way for this capability are able to discriminate numbers or numerosities, as we say.
Yeah.
And that starts with insects, spiders, fish, amphibians, birds, and mammals, to which we are also belonging. So all of these very different groups of animals, to one way or another, have a rudimentary capability to deal with quantity information.
Right. When did it start? Do you know, like, what was the first species which had this function? Do you know?
Yeah, that's kind of a problem in evolution.
Yeah, we don't have much of them left.
Right. We can't easily work our way back. I mean, Ideally, we would like to have the species around that lived hundreds and millions of years ago.
Right.
But they are extinct. They are no longer around. So we can only try to find out based on the relationships, the phylogenetic relationships along the evolutionary tree of life, to find out what might have been the first common ancestor of different groups of animals that may or may not had possessed these capabilities already.
Yeah. And what's very interesting about this is of course what is the benefits to a species to be able to discriminate about how? Yeah.
That's a very interesting question. Again, for biologists, it's very clear. Behaviors and all sorts of traits that we find in animals would only survive and become passed on to the next generations if they are beneficial for the area, for the individual, or less radical, at least not detrimental. Yeah. But usually they should be beneficial. So according to this logic, understanding numbers and discriminating numbers should have a benefit for all sorts of animals. And there is, by now, plenty of evidence, really, again, from all these different branches on the animal tree of life, that animals have a benefit if they are able to discriminate numbers. For instance, when foraging, right, almost all animals go for more food items than for less food items. And we immediately understand that this is beneficial for survival, right, to have more available and less. Other examples are in seeking shelter amongst group of animals, like fish do this when they're schooling, and they look for bigger clusters of fish to seek shelter. Or in social interactions, there is this dictum, there's strength in numbers, and that's particularly important in social interactions. So it's known that animals first explore the number of individuals in their own party before they decide whether they respond aggressively or respond passively and retreat when facing an opponent party.
Right.
Chimpanzees do this, lions do this, all sorts of animals have been shown to estimate the number of individuals before they decide how to behave. And in all of these behaviors, it's very obvious that the animals have a benefit. It helps them for surviving.
Yeah. That sounds very, very logical. That if you're let's say if you're a predator and you're out there on the savannah and perhaps you see some prey standing alone somewhere, then that would be a lot easier than if it's a horde of animals which can harm you.
That's right. Yeah. Another nice example is wolves. They hunt in packs, and the size of their packs the number of individuals in the packs is according to the type of prey that they are hunting. So if they are hunting elks, for instance, then the number is smaller than when they go for bisons, which is the most formidable prey that they could hunt in North America. So wolves obviously determine the group size of the hunting party according to the strength of the prey they want to hunt down.
That's interesting. So if it's a lone wolf, they will do a lot different. They will hunt a lot different things than if they're 20.
Usually wolves would hunt in packs.
Yeah.
Very social animals.
I was just thinking if there were like an outcast or something.
Maybe it should go with a mouse.
Yeah.
Or a hare.
Yeah, probably a hare. I think that they're quite fast though, aren't they?
Of course, yeah.
But wolves are fast. Okay, but it's quite interesting. So it really depends. Also, I mean, it's when it's these bigger, more advanced animals, it's quite logical to that predators, for example, or also perhaps also other animals that perhaps if they see one lion somewhere, it's not much of a threat perhaps, but if they say 10 coming or lying there, then they should better stay away from there.
Yes,
also.
Exactly right. So this is an example of territoriality. Many animals have their territories that they are guarding and defending, and of course there are always intruders. And it's known from lions and from chimpanzees that when they are patrolling the borders of their territories, and then usually they would not see, but hear opponent parties and individuals that potentially would enter their territory.
Yeah.
They determine the number of these opponents based on the sounds that they are hearing. Mm-hmm. That has been with playback experiments, for instance. And then again, they decide according to their own strength in their own party whether they can afford to respond aggressively and chase these intruder away, or whether maybe it would be wiser to retreat for the moment.
Wow.
And not risking to be injured, because these interactions can become very violent.
Yeah.
Particularly in chimpanzees. So it's known that chimpanzees can even kill one another if they enter such aggressive contests.
Yeah, nature is fascinating.
Yeah.
And also so in this example that you spoke about before, it's being able to hear a sound, and then you use that information and link that to this number, to this.
Yeah. So again, this is investigated with playback experiments where scientists have taped sounds of lions, and they can then play only one lion, or they can play the sounds of 3 lions together. And this is something that the hearing animals realize, and from the sounds they can estimate the number of individuals they are dealing with.
Right. Okay. And yeah, that's fascinating. But if you would compare this, if you would compare humans to other species, how does this ability differ, or what would you say?
I think overall, as long as we are not learning to count and do real mathematics with number symbols, these capabilities are very similar and comparable.
Yeah.
Yeah. And this has also been shown by very fascinating studies with indigenous people in the Amazon region, for instance, in South America. So there are fortunately still cultures who, for whatever reason, did not evolve real numbers, and they cannot count in our sense, but they can still discriminate the number of objects in this approximate non-verbal, non-symbolic way.
Right.
And when analyzing the performance of the people, so what they are really doing when discriminating nuts or batteries or what have you, then the performance looks almost identical to what an animal or an infant that had not learned to count would do.
Right. So this innate ability is something that all of us have, even if we have learned numbers or mathematics in school or not. We all have this innate ability.
We have it, and we can. So it's overshadowed as adults in our culture, at least, because we would, of course, count if we have specific tasks, specific quantitative tasks. But there are tricks that can suppress for a while our counting capabilities. One of them is, for instance, to present the stimuli very, very rapidly so that we are not able to count, because counting an individual object takes about 150 or 200 milliseconds. So for every single object that we would count, we would need this additional time. And if we don't have the time, all we can do is to estimate the number of objects in a set. And then we still rely on this primordial capability.
Yeah, because this is a lot faster, right? This intuitive system compared to the counting system.
Much faster. It's very perceptual, if you like. And it's not a sequential process. At least it does not have to be a sequential process, while real counting happens in sequence. So it's 1, 2, 3, 4, 5, while estimating number of objects can be very rapidly.
So one example would be, so let's say if you're having a screen and if you have like 6 dots or something, it's quite that you have this system which immediately just gets it that, okay, this is 6 dots. But
and we have and we have shown this in monkeys, that monkeys don't need any time.
Yeah.
They decide immediately. They don't move their eyes, they don't need additional time. So no matter how large the number of objects is that they are facing, they do this basically in an instant.
But it's also, this other system takes a longer time. So if there would be, let's say that if there would be like 50 dots, then would this innate base system be able to get that it's 50, or then we'll have to count it if it's that many? Or
that's a very interesting question. The thing is that this intuitive system, what I call the number instinct, or what has been called the number sense, is relatively precise for small numbers, but it is getting progressively less precise with higher numbers. So, and with this system, that really is, it's an estimation of the number of objects. With this system, we can't represent 50 precisely. It will always only be approximately 50.
Really? So you mean if it's 40 or if it's 60, you will still say that it's 50, kind of, or?
Whether it's 45 or 55.
Yeah.
It is about 50.
Okay. Yeah, okay, I get it, yeah.
It's really an estimation. I think estimation would be the best expression for this system.
Yeah. It also seems quite logical that, I mean, if you're before, it would probably be important to be able to count 5 or 6 or 3 items, because that is something that you will probably get in touch with quite a lot. But it's not that often that you perhaps meet 100 of different items if you're out in the wild, like evolutionarily speaking.
That's exactly right. And from an evolutionary point of view, the idea is that this is also an adaptive trait, or a trait that helps animals to survive, precisely that they are able to discriminate small numerosities relatively precisely, because this is usually what is relevant in their natural habitat from an ecological point of view. It matters a lot whether they are facing 1 or 2 or 3 different items, or companions or food items or whatever. It's not so important to discriminate 50 from 40 individuals. Yeah,
sounds very logical.
Because if you imagine you as an individual, you are facing a certain number of enemies. It's important to discriminate whether this is 1 or 2 or 3 enemies, but whether it's 50 or 60 doesn't matter. You have to get away anyway.
It's true. It's better to know if there's 2 two gorillas coming at you or if there's 50. Because if there's one, then you probably stand a chance. If there's two, you're probably screwed and you should get the hell out of there, kind of.
Yeah, exactly.
And if it's 49 or 51, it doesn't matter because you still got to run. Yeah. You got to run for your life.
Precisely. That's exactly the reasoning behind it, yeah.
That's super interesting. But so it's quite logical when it is these bigger species. But you said that you can also see this in insects, for example, in spiders. Like, what is it? The same adaptive benefits that you get there, or?
Yes, the idea is that they get exactly the same adaptive benefits in their specific environment and in their habitat. Of course, they have different foraging strategies and so on and so forth. Like if you think about bees can be terribly smart animals.
Yeah.
Even though they have less than 1 million neurons in their brains. But sometimes these are amazing creatures. And bees, for instance, have also been shown to discriminate the number of objects. And most recently, it's been shown that they even understand the empty set, or if you like, the precursor of number 0.
Yeah. That's fascinating. It's a really cool thing. But I was also thinking about, like, is there any species that automatically can count 50 or 51 where that has been super important for their survival?
No, I'm not aware that this has been reported, and I would be very surprised. I would be very, very conspicuous if any animal could discriminate 51 and from 50, because again, this is really something that only kicks in with our symbolic counting capability, which provided us with an unprecedented precision of dealing with numerical quantities. And then also, of course, being able to do calculations. That's something that I don't see in animals, really.
Yeah. Okay. So we as humans, we use this, like if we were walking down the street, we perhaps see one person coming, but then we see 5. And then this intuitive system is like, okay, there's 5. So this, this can mean this can mean something else than if it's just one. And also, like if we're out there picking blueberries, for example, then it's also like, oh yeah, then it's more perhaps this estimation thing. There's like, here is a heck of a lot of blueberries, or it's not so much blueberries, perhaps.
Yeah, I think we humans also do this all the time. And precisely in these situations, as you just mentioned, where the exact number is not important.
Yeah.
Why would we go through the pain and count 100 blueberries if it's not important, right?
Exactly. But it's perhaps good to know that this is a good blueberry spot, or this is a bad blueberry spot. So like it's more than these scales than like medium, large kind of.
Yeah. So comparison between numbers of items, but that's also possible with this non-symbolic system, with this number instinct. Again, it's not extremely precise, but it's possible and good enough, I would say.
Yeah, cool. But okay, so this is kind of the foundation. So how is this linked to using mathematics and the things that we learn in school?
Yeah, there are a couple of very basic behavioral signatures or behavioral characteristics that can be seen in both of these systems. One of them, for instance, is the so-called numerical distance effect. That means that it is easier for us to discriminate numbers that are relative to a given number further away, or larger and larger compared to a given number.
Right.
So, for instance, discriminating 4 and 5 is relatively difficult, but discriminating 4 and 10 is easy because the numerical distance has increased. That's something one can see in both of these systems. So even if we are counting symbolically, it's been shown that we need a little more time to tell whether the numeral 4 and 5 is different compared to the numeral for 4 and 9, for instance.
Right.
Depending on the numerical distance.
Right. Interesting. I just think it's so fascinating that we have these. I mean, this is just one of our built-in systems. It's so fascinating that we have, I mean, thousands and thousands of different built-in systems to be able to live in this objective world. It's just it's such a fascinating thing that just this thing that I think most of us just take for granted, being able to discriminate between 2 or 3 dots, is something that is actually being developed over millions of years, and is something that we have a physical structure in the brain, which actually is which is its job to do this. It's just so fascinating.
Yeah, some people have called it a startup toolkit, and I think that's a very nice expression.
Yeah.
So rather than having to learn everything anew, which would be very time consuming, certain basic capabilities seem to be built into our brain.
Yeah.
And we can then build on these much more elaborate skills like true counting.
Yeah, but and this system, do we have to have this system to be able to do math?
I would say yes.
Okay.
But it's very hard to prove the opposite, right?
Yeah, for sure. It's hard study.
We all start out with such a system.
Yeah.
I have never heard that someone would not be able to estimate the number of objects. So it's very hard to demonstrate the opposite.
Right. Yeah, for sure.
But or put it the other way around, everyone who is able to count started out with this number instinct.
Yeah.
So probably there's a causality between them. There's probably a reason why we start out with this system. Yeah. And there's a reason why this has been evolved over hundreds of millions of years in evolution.
Yeah. To have this.
I guess we need it. I really guess we need it, because I don't see any other system that would provide us with the notion of what a numerical quantity means.
Yeah.
You see?
Yeah. It's so it's just so fascinating how we this is just one of the thousands and thousands of different features. It's like if you buy a new iPhone, you can call with it, you can text with it, etc. But us as humans, we can just do so many complex things that still is so hard for the most advanced robots to do. At least to do, being specialized in doing so many different things so well.
Exactly right. I don't see any machine that would be able to compete with us also in the near future. And that's what's, of course, fascinating about the human brain in particular, right? It's just a fascinating, brilliant device.
Yeah.
It, of course, was initially made to help us survive long enough.
Yeah.
And now we can do all of these, excellent mathematics and go to the moon and what have you.
Yeah. Yeah, and also that we can build. I mean, we both have this biological foundation, but we also have knowledge and being able to improve kind of our software or improve knowledge upon each other. Yes. So we can achieve all these great things.
It's exactly right. Yeah. And in terms of mathematics and true counting, this is really like having a new software in the brain.
Yeah,
it's a huge difference, but it needs this basic initially to arrive at this point later in life.
Yeah, that's a really good analogy, I think. So you have this intuitive foundational system, and this is kind of more of, and the mathematics part is more of a software upgrade than a biological upgrade, even if you of course stuff has to happen in the brain for you to be able to learn this stuff, but still it's more of a software upgrade perhaps.
Yeah, it's a huge software upgrade. I think it's a game changer. It changes everything.
Yeah.
But it starts out with this very humble beginnings. Yeah.
With this little starter pack.
Yeah.
Yeah. Is there also is there any research if there's a big difference between us human beings of the system?
In terms of
if some people are better at this, or some people are less good at this.
I understand you. Yeah, There are, in fact, many investigations, particularly related to problems in school. So it's known by now, for instance, that about 5% of average of the children in school have problems in dealing with numbers and mathematics, not because they are lazy or stupid, but because they have obviously slightly differently wired brains.
Right. Yeah.
And it can be really diagnosed today that such children or people, they are called dyscalculics.
Okay.
So this would mean that they have a weak or a weaker capability to deal with numbers.
Okay.
This can really be diagnosed, and of course, there would be there's a great need to help these children or people in their everyday life and to learn mathematics. So yes, there are differences between individuals. There are, of course, some individual characteristic differences. Not every one of us is becoming an Einstein, obviously. But beyond that, there are also some, pathological modifications of this capability that are particularly interesting and need to be understood better, what's happening in the brain, to be able to develop devices or strategies to help these people better in life.
For sure. Is this also? I've been studying in a student city in Sweden before, and I think it was quite straightforward that people who were engineers, they were more just made for doing math. At least that's in my point of view, than other people's perhaps. It just on a group level in general. Would you say that is that something? Does this have something to do with this as well? That some people are just wired to be able to do math and do these kinds of subjects better?
Partly, yes. I definitely would not say that's everything, but based on developmental studies, particularly in twins that may or may not share 100% of the genetic makeup, it's been shown that at least to some extent, we are genetically equipped with better or worse capabilities of dealing with mathematics. And that's, of course, important to know. However, one must not forget that about 50% of this capability cannot be explained by genetic differences.
Yeah.
And this is, of course, also the point where education could kick in and where also a certain amount of hope can be generated, because that allows them now to develop specific teaching programs to help people who struggle with mathematics and numbers to become better.
That's a really good point. So there seems to be a biological component, but this is something that we can work with. So if you're dealing with problems with mathematics, then you can learn to become better.
Right. And compensate at least part of these difficulties. Probably not all of them, also depending, of course, on the severity of dyscalculia, but at least part of it. And that alone would be a huge benefit for the individuals. Right.
And it's also quite interesting that we have been talking about this also, but that it really seems to be rooted in the brain.
Yeah.
Could you also just give us an overview or a summary of the biological foundations for this system?
Yeah, I think one of the first questions was when talking about the brain, where in the brain could be centers for processing numbers or doing mathematics?
Yeah.
Or even put more simply, are there at all some centers in the brain, or is it the entire brain that's doing this more or less? And I think right now it's quite clear based on many, many studies that there are some centers in the brain one is called the posterior parietal lobe, and another one would be the prefrontal cortex. These are particular areas in our brains, in the cerebral cortex, that are sometimes quite specifically engaged when we are dealing with numbers and crunch numbers. The first evidences historically actually have been made with patients that suffered from brain damage in these areas. And many of them developed very peculiar and very specific deficits in dealing with numbers. So, for instance, I remember one patient who had a damage in one of these specific areas, and after this insult happened, was no longer able to understand numbers larger than 4.
Right.
So she still was able to count up to 4, but everything beyond 4 was simply gone, was erased from her understanding.
Could we talk a little bit more about this, just so that I and the listeners really understand? So, could you elaborate on this a little bit? So it's the person could, if there were 4 dots, then the person could count 1, 2, 3, 4. But if it was 5, then the person couldn't count any more than 4, or how was it working?
Exactly. She stopped at 4. She could not count beyond 4. So 5, she said something like, "This escapes me now," or "This escapes my mathematical capabilities."
Okay.
And it's probably a little hard for us to imagine this, but based on these reports, this entire grasp of what a number beyond 4 means was gone, was simply no longer existing.
Yeah.
And this was, as I said, based on some insult, some injury of a specific part of the cerebral cortex of this patient. And there have been several reports of such patients where these patients developed such specific deficits. And maybe to add one thing, one of the very important messages from these patients is that usually they are still able to speak properly and use language.
Yeah.
So this strongly indicates, and I think this has been confirmed with many other methods up to now, that our capability to do mathematics and to do counting symbolically is not the same as a language system, is independent from the language system also in our brain. Because many people still think, and I understand why they think it, because we first, usually as children, we first learn to talk and then learn to count. So it seems intuitive that that counting and mathematics is maybe part of our language system. But that's not the case. It is a separate system, a separate symbol system in our brain. It also has its separate brain areas where it is processed.
And then it gets connected.
It is connected, of course. I mean, we are using speech and language also to utter mathematical findings and processes.
Yeah.
But it's very illustrative.
Yeah.
To hear about patients again that either have no problem in speaking and using language, but have huge problems in doing mathematics and counting, or vice versa. So there are also other cases where people have, it's called an aphasia, so a deficit or in speaking or language inability, but they are still able to do sometimes surprisingly abstract mathematics and algebra, which are also using semantics and syntax just as language needs.
So there are these different systems that are specialized in doing different tasks.
And again, it's also represented in different parts of the brain. And maybe if I can add something,
for sure.
Even in a more local level and more microscopic levels, at the end of the day, it's the nerve cells, the neurons in our brain that are doing all the jobs that based on their electrical activity. And we know now that we have specific neurons in our brain that are specifically tuned to a given number of objects. So say there are neurons in our brain that are most active whenever we see 3 dots.
Really? Okay.
Or beer cans or sounds. And they are less active when it's 2 or 4, and they are not at all active when it's 1 and 5 or higher. So neurophysiologists say these neurons are tuned to a specific number.
Wow. So some of them are like, I am the number 3 neuron.
Exactly.
My entire existence is all about whenever there's 3 things, I will say there's 3 things. It's quite an interesting existence, isn't it? Like your entire thing you're doing is just 3, and then everybody's like, yeah.
Well,
it's too bad when there's never 3, and then that neuron will be really depressed.
Maybe it takes a nap.
Yeah. Yeah, it takes a long nap. Yeah, but that's fascinating. Is that particularly with these lower numbers that there's more neurons for them, or?
Yes, that's another aspect. Exactly right. So there are many more neurons that are dedicated towards these very small numbers like 1 and 2, and there are fewer and fewer neurons that are representing, as we say, or signaling the higher numbers, which also can nicely be reconciled with what I said earlier, namely that animals and we are much better at discriminating small number objects compared to large numbers of objects in this approximate system.
Yeah.
So this would be a neuronal foundation, if you like, or a neuronal correlate of this behavioral capability.
Yeah. There's also you have also written about the title or the title of this part of your book is called The Magical Number 0.
Yes,
which of course makes you curious. so like what is so special about 0 and the magical number 0?
Yeah, 0 is really a hugely interesting number. For many, many reasons. So one of the reasons is that for us to understand, or for animals and us to understand 0, is to go away from the empirical world or transcend the empirical world.
Yeah.
Because when you think about the natural numbers, 1, 2, 3, 4, 5, and higher, that's something we can actually deal with. So we go out to buy 3 fish, but no one of us goes out to buy 0 fish, because
that would be weird.
that's just no longer existent actually in the natural world.
Yeah.
And historically, to read up how long it took mankind to actually become aware of this, that an empty set, the numerosity 0, can still be a set or a quantity, even there is no item in this quantity, took mankind almost forever. Yeah. And then further realizing that an empty set corresponds to the number 0, that only was realized in the 7th century in India. So it's an extremely recent insight that there can be a number 0. And now, of course, if you think about this, we need the number 0 first to understand that there can be also other numbers, negative numbers, or all other kind of weird numbers that are no longer related to the natural world. But we need these numbers desperately to have a full-blown number theory and to do all sorts of calculation. Without a 0, all of this is not possible. And the entire field of mathematics was dramatically hindered by the lack of this discovery.
Wow, yeah. So just to make this clear, so we're really made to be able to, and we also have like neurons specifically for these numbers, so 1, 2, 3, 4. So we can see like three dots or 4 dots.
Yeah.
But we don't have a 0 neuron in the brain in the same way to find things in our environment, in our everyday lives. We don't have that capability. Or
we probably don't have 0 neurons right away from the beginning, but we can of course learn to represent number 0, and then we do have such neurons.
Okay.
Even animals can be trained to realize that an empty set is relevant for them, and an empty set is something else than one dot and two dots and so on. And they can learn this, and that has been shown. And in these instances, we do find neurons that are then representing even empty sets as a numerical quantity.
But is this, because this this is fascinating, but is that also in the same region in the brain as these 1, 2, 3, 4 neurons, or are they in a more like an abstract part of the brain dealing with more of this?
They are actually in the very same regions.
Okay, yeah, that's okay. I thought it would be more of the, okay, yeah.
The regions that we are talking about, they are the most abstract parts of our brains of all. Okay. So when you think about logic and so on and so forth, these are the most abstract capabilities that we have, including mathematics.
Yeah.
So we can't go any higher than, for instance, the prefrontal cortex. That's as good as it gets in terms of computation in our brain.
Yeah,
so we are already in these high level areas, and that's where also the zero will then be represented. And probably also negative numbers in our brain, but we haven't investigated that yet.
This also makes me wonder, do you think that is there something good for I mean, for us, I understand it's good to be able to do, I mean, we must be able to do our mathematics and stuff, but for other animals, is there any benefits to understanding that there's zero or none?
Yeah, I think, I guess so. There would be an understanding, maybe not yet for a numerosity zero, but understanding absence versus presence of something is also important for animals.
Yeah.
So understanding that there is a food source present or not is terribly important. And from that, it's a relatively small step to understand that the absence of something could be a quantity. A quantity that does not contain any elements anymore, but a quantity that is next to one.
Great. Okay, it's been really, really interesting talking to you about this, and if somebody wants to check out your book, it's called A Brain for Numbers: The Biology of the Number Instinct. So a big thank you for coming on to the show.
It was my huge pleasure. Thank you very much.
Okay, thank you so much.
Thanks.
Hope you enjoyed the episode. Friends, I really need your help. I'm trying to get the podcast out there. So I was wondering if you could help me by leaving a positive rating and a review on your Apple device or the podcast player that you're using, as well as subscribing to the podcast. That really helps getting the show more visible on iTunes and other players. And if you don't know how it's done, then YouTube has a lot of great videos, so you can search there. All right, that's it. Take care.